Hello everyone. Today we will be presenting our work on model compression. This is a work done during internship at Microsoft. Modern neural networks like Llama 27B are massive, requiring about 28 gigabytes of storage and FP32 precision, making them challenging to load and slow to run. To address this challenge, one either applies pruning or quantization. To further compress the model, we consider a joint approach to combine the strengths of both techniques in a unified framework. There are a couple existing approaches that combine pruning and quantization together. One line of work applies a two-stage strategy, where pruning and quantization are applied independently. This method is inefficient, as it overlooks the trade-off between sparsity and quantization. Some recent work explores joint approaches, but these often focus on unstructured pruning, which is hardware inefficient. Moreover, existing methods like Bayesian and variational approaches are primarily designed for CNNs and do not generalize well to transformers. To overcome these limitations, our work proposes a joint pruning and quantization framework that integrates both strategies efficiently and automatically in one-shot training manner. Our framework addresses an optimization problem with both sparsity and layer-wise bit width constraints. We start by converting the full model into a quantized model, then construct a pruning search space using dependency graph initialization and optimization. Next, we jointly apply pruning and quantization. Finally, we train the compressed model to convergence. Our first step is to convert the model into a quantized version, focusing on two key aspects. First, we quantize layers with significant parameter counts, such as convolutional and linear layers in CNNs, while excluding others like batch normalization. Second, rather than using uniform bit width quantization, we learn layer-specific optimal bit widths by introducing trainable quantization parameters, guided by each layer's sensitivity. Once we've got our quantized model, we need to set up our pruning search space so it fits into the joint pruning and quantization stage. First, we kick things off by setting up a dependency graph to figure out which parts can be removed. To get this right, we need to understand a few concepts: removal structure, minimal removal structure, and zero invariant groups. A removal structure is just a part of the model that can be taken out without losing the architectural validity. If this structure doesn't include any other removable structures, it's called minimal. Zero invariant group is a class of minimal removal structure. They're special because if their input is 0, the output will also be 0. This means we can safely remove parameters that are 0 without losing any useful information. We decompose the dependency graph into zero invariant groups, categorizing each as important or redundant based on their significance. Redundant groups are progressively pruned. The addition of fake quantization layers renders the initialized computational graph incompatible with the pruning framework. To address this, we perform graph optimization that leverages the unique characteristics of weight and activation quantization. This produces a quantization-aware dependency graph that is fully compatible with our pruning scheme. This is the workflow of the joint stage. We first warm up all trainable variables to reach a good initialization point. After that, we establish an interactive relationship between pruning and quantization. In the end, we continue the training process till the end. The joint stage faces two challenges, the first being the bit width constraint. To address this, we propose a partial projection method, applying the projection only to the quantization step size d. This choice improves training stability, as gradients with respect to d are less prone to exploding or vanishing. Another challenge is integrating pruning with quantization. To tackle this, we start by examining the update rules used for pruning alone. Our approach leverages zero invariant groups, categorized as important or redundant based on saliency scores. Important groups use standard stochastic gradient updates, while redundant groups progressively forget their information, transferring some of the lost knowledge back into the model. A forget rate controls how much redundant information is discarded. However, our current selection rule doesn't consider quantization parameters. With fake quantization layers, information is stored in quantized values, so the forget rate should also account for these. Therefore, we need to revise the update rules for both the forget rate and quantization parameters. Further details are provided on the next page. Our forget rate and quantization parameter selection rule is motivated by the search direction is always a descent direction with respect to loss function at the current iterate. After mathematical derivation, we establish the reciprocal relationship between forget rate gamma and quantization step size d. This relationship implies that if a small amount of redundant information is removed, we consider high bit width for quantization. We evaluated our method on CNN architectures, comparing it to competitive approaches that combine pruning and quantization. The comparison focuses on two metrics, TOP1, test accuracy, and bits of operations, BOP, which measures the bit complexity of executing a model. Notably, some existing methods only address unstructured pruning, which is less hardware efficient than the structured pruning we adopt. Although our method yields slightly lower test accuracy in some scenarios, it remains competitive due to significantly lower BOP and the use of structured pruning. Next, we conducted experiments on transformer architectures. We test the Bird on Squad dataset and Phi2-2.7b on common sense. As indicated in the figures above, Geta is significantly better than two-stage processes, first prune, then quantize, in terms of both accuracy and compression ratio. To summarize, we proposed Geta, an automatic framework designed to jointly apply structured pruning and quantization-aware training to deep neural networks, addressing key limitations of existing methods. For more details, please scan the QR score below. Thank you for your attention.